relevant to the algorithms, to the programming, to the software development in general. So the floor is yours.
Hi, everyone. I'm Samuel Richard. I am a second year in the software engineering degree here at ETS. I'm also vice president and co-founder of the ETS Quantum Computing Student Club. And I am today accompanied by Simon.
Yeah, so my name is Simon. As I said, I'm a sophomore in software engineering. I've done a lot of internship in software development, like at the Canadian State Agency. And I've also done some research internship at Sherbrooke, where I've done like quantum machine learning research. So we are both well versed in both domain, at some extent, obviously, in the quantum computing and software development. I would like firstly to extend my thanks to the académique group to have invited us to present today. We obviously always like to share our knowledge about the quantum industry and quantum computing. We don't often do it in front of people of your stature, so we're really grateful for this opportunity. Simon will talk a little bit more about the club, what we do, our activities, and then after that, we'll proceed with some of our own experience with the software development in the quantum industry or in quantum computing. So Quantum ETS, it's a club that we both founded like 2 years ago. There's multiple missions to the club. The first one is education. Education, so what we do, we host workshops that we present what can we do with quantum computer, what are the main applications, why should you be interested in that field. We also host Q meetings. So Q meetings basically is just like everything in quantum. When you do something with them, you put the Q before it. But essentially, it's just a meeting that we invite researcher, industrial partner, or like anyone that have relevant project or subject to talk about during like the lunch break. Also, another of our mission is to do some convention, and this is the most important part for. That's why we are here today. It's because we developed through the years some experience in like quick quantum computing software solution development. So we've done several hackathons, like almost like 4 each year. We've done the Canadian Quantum Cup, where we finished first in Quebec. We've done QAC, which is a worldwide online event for quantum hackathon. We went to Zurich, Switzerland, to do another quantum hackathon, which was more focused on use case. And we also developed a community in Montreal around quantum computing. So we try to foster like students that are interested in that topic. So we do research for internship for them. We help them to contact to academic partners. We match grad student to undergrad. And we also have some social activities, like you can see over there. So why quantum? Why are we interested in the quantum computing? So far, there's not really a real use case for quantum computing. It's more like potential benefits. So we think that quantum computing might be useful in simulation, in some quantum algorithm. Like an example will be fertilizer production. This fertilizer production can consume up to like 1 or 2% of the global energy consumption. So this includes like travel and transport industry and stuff like that. So we think that with a quantum computer, we might be able to come up with a better process to synthesize fertilizer. And so there's a lot of like use case like this that will be a big game changer. So that's why we're interested into that field. And there's also like other fields like financial modeling, cryptography. This is the one that is the most interested by the government. So, example, NSA and the CIA and much agency like are investing a lot because of this. Because we have a quantum computer could break RSA and a lot of like optimization. So this is like all potential use case, but we don't know for sure. What we know for sure is that quantum computing provide us with new set of tools like entanglement, superposition, that allow us to come up with new algorithms. And so with those new tools, we think that we might be able to resolve in a lower complexity those kind of problems.
Without giving you a history lesson, I would just like to remind everyone about where is this whole field coming from, where is it at right now. So unsurprisingly, just like classical computing, the whole field has been founded by mostly people that were like coming from physics or mathematics background. And the thing is, today, quantum computing is still a very young field, and most of that field is still dominated by physics engineering, and mathematics. We are seeing right now a growth in the software engineering experience or the software engineering workforce, although it is still a minority. So all the standards right now are not really there, but we already have quantum computers today, and it is thanks to those people, those geniuses of the past centennial that brought us to where we are at today. So a couple decades later, we still have a very small number of algorithms. Amongst the most famous ones, we've got the Shor algorithm for cryptography, and we've got Grover's algorithm for research in a non-organized list. We've got big players that can claim that they have over 1,000 qubits. The thing is, there's still no real scalable way to deal with errors in those 1,000 qubit machines. So yes, we've got many qubits, but there are still so many errors. So again, no real application for those machines yet. There is no real, true, high-level programming language still, as Hassan said earlier. We're still doing assembly, and we'll see why a little later. And most of the efforts right now is spent on improving and building the hardware, trying to scale it, trying to correct the errors in the hardware. Not so much on software, exactly, standardizing the software side of things. In the workforce presently, I'd say there are two categories of software developers. You've got the classical software developers, and you've got the quantum software developers. The classical software developers are like you and me. They know how to build large, scalable, flexible, agile, and maintainable projects. They know how to deploy them. They're using trialed techniques and methods, whereas quantum software development is more coming from a physics and mathematics skill set, and they're better at dealing with the intricacies of quantum hardware, such as error correction, error mitigation. They're the ones designing the algorithms, and if we compare it with classical software development, for example, if I have access to a quantum computer via cloud or some API, that would be the classical software developer that does that job. If I was to draw a Venn diagram of those two categories, there would be a common effort at building a high-level programming language. I said there is no such thing, but there is some effort that is spent on that right now. So how does it look like a high-level programming in classical computing? You all probably know your Python, your JavaScript, your TypeScript, all those very high-level programming that doesn't require any knowledge about the hardware, any knowledge about the machine. You don't have to manage your registers. You don't have to optimize your code. And we had talked about C language earlier, and the the advantage of still using those language. And there are also pros for high-level programming such as Python, but I want to highlight that there is even a higher level of programming, and I'm thinking about Scratch here. I'm thinking of a high-level programming that can be discovered and explored for a high schooler, for example. So somebody that the abstraction is such that a high schooler can tackle algorithms and try to implement solutions with blocks and puzzle pieces. So that's what I have in mind when I'm thinking about how far we've come with high-level programming. In terms of quantum computing, we do have Python, but we're using Python to design circuits. So what we're really doing is we're just telling what operations we want to do on the computer using a high-level programming language. But the task that we're doing is not high-level. It's very low level. It's very close to the hardware. The only thing that most people they don't need the knowledge for is how are those operations acting on the qubits on a specific hardware. So when we're saying high-level programming, we're thinking about using just a language to build your circuit, and then after that, the firmware, that's the part of the stack that you don't need to know about. I'd like to mention that IBM on their website, they've got a tool that's called IBM Quantum Composer, which is a graphical interface. So we could technically say that it is a high-level programming technique, but you're still doing assembly. So the task that you're doing, that you're achieving, is still low level. You're just using high-level tools to do so. Amongst the high-level languages out there, which are really just frameworks, we've got Penylane, which I will be discussing a bit more later. We've got Qiskit that's been mentioned plenty earlier. That's been developed by IBM. Cirque that's developed by Google. Penylane is, by the way, is developed by Xanadu, a Canadian startup based in Toronto. And we've got some others, some other packages that are available in Julia as well. So two languages that are, it is not a coincidence that are really related to the computer science field and data science. And really what we'll tackle now is our experience with those tools.
So as a student club, the main experience we have gained over the years is like the hackathon experience. We think that hackathons, for now, at least for quantum computer, is a great resource to develop quantum programming language. For companies, especially because this increases the visibility of the language. This also create a lot of codes for example, other students to learn or generate generative language model to take in. Also, this allows libraries to be tested. So example, in some competition, we discover some bugs, we created some issue, and then the company fixed the bugs later on. So this is a way to stress test the library that they use without having actual real hardware and real like practical use case. This is some way to develop the product. So for the development workflow, there's not really like a standard way to develop a quantum algorithm. So for now, it's just like you are reading some papers, you're trying to match what we are doing classically. So those hackathons can help to standardize the pipeline, as like a lot of students will try to come up with different solutions. So they will explore a lot of like possibility of like how should we example connect the classical and quantum power together. Also, this is really interesting because there's a lot of tool development that can come by doing those hackathons. So example, there's some resource estimator. So often it's hard to like develop to know how much example qubit or how much whatever metric do you use, it's hard to know beforehand, before doing it, what you'll need as quantum resource. Also, there's some integration with Jupyter notebooks that are developed, some tools for simulation, and other tools, other algorithms. So as a concrete example, at Zurich, what we developed is a cleaning, it's a way to clean the ocean with a quantum algorithm. So basically, cleaning the ocean is really a problem that matters a lot because currently, as a society, we throw a lot of garbage in the ocean. And so we are starting to see some island of garbage. We can even saw them using satellite imagery. Like here, you can see a bunch of dots. Those are small area where the garbage, the plastic density is higher than it should be. And this creates a lot of issues plastic degradation can cause problem with fish and other wildlife animals. So the problem here, as some of you may have, may think of a solution, will be to use a traveling salesman kind of solution. But the thing is that if you increase the complexity of the problem and want to be more efficient, adding multiple votes, you need to handle a lot of cases. And so quantum computer right now, you don't have a lot of algorithm. So you need to find a way to utilize your resource properly. So when you're trying to design an algorithm, you have multiple things to consider. First of all, the hardware resource. Hardware resource, currently, we don't have big quantum computer, and those are really noisy. This is the example of the quantum computer that we have here at ETS. It's called Monarch. And there's only 24 qubits, but usually in the industry, we can see some quantum computer about 100 qubits, even 1,000 qubits, but the majority of quantum computer are closer to 100. And the simulator, we cannot scale a simulation up to 30 qubits, so we are really limited to what we can achieve as a project. So we got to compose with that. Also, there's not a lot of quantum algorithm. Developing a quantum algorithm is really hard because it involves not classical thinking. We need to come up with solutions that we are not born to play with them. And also, we currently cannot test them, so we need to theorize them and to make sure that to have some theory that push them forward instead of testing something, instead of having some heuristic. Also, as I said, the quantum algorithm right now are limited by the circuit depth. So we have wonderful algorithms that are coming in the future, like Shor's algorithm to break RSA. We have other really neat algorithm to, example, estimate perfectly the energy level of some molecule and stuff like that. But they are out of reach for right now. So what we need to do is to find alternative, variational circuits that don't have a huge depth. They don't have a lot of steps to be realized. So we have all of that to take into consideration. And one more thing is that when we are trying to distribute amongst multiple quantum computers, there are some problems that arise. Example, when you try to devise a quantum algorithm into multiple quantum computer, the performance ratio is not necessarily the same. So example, if you take a problem that have a data input of 100,000 and you split it amongst multiple quantum computer, the gain that you will have by using multiple quantum computer reduce the quantum advantage that you would have if you only use one quantum computer. So there's really a lot to think about. And so yeah, for the solution that we come up by, so we try to use hybrid quantum and classical algorithm because that's what is trending right now since we don't have a lot of hardware resource. We use Qiskit, CUDA quantum to simulate the quantum computer, and MPI, which is a distributed quantum library, not quantum, but classical library that can be used to work with quantum computer. And we use a divide and conquer approach where we add a graph here. We use the classical K-mean to cluster the data, and then we send the clustered version of the problem through multiple quantum computer where they each solve the problem individually using quantum algorithm, which is called Queway, and a max cut formulation of the problem. So what we are doing the divide and conquer here with the classical clustering. Once we have that, we convert the problem to a graph that is like a cubo problem. Maybe you've heard of that. And also, once we have that, we transform it to an equation that can be understood by a quantum computer. And we have a bit string of result of probability that leads us to the best answer that we are looking for.
So the other project that a member of the club, myself, had the chance to work on was developing a penny lane plugin to interface with Monarch. Monarch, as we said before, is a quantum computer. It has 24 qubit conducting architecture for people who are curious. It's owned and managed by Calcul Québec. It's sitting here at ETS in the D building's basement. It is built and developed by Onion System, also a Canadian startup. And to the way we access it, or we send our operations to the computer, is using Snowflake, which is a Julia framework. PennyLane is a quantum computing framework coded in Python, and it has very good software building features. It has been developed with chemical simulation and machine learning and optimization in mind. It is hardware agnostic, so it can be used with a very diverse scope of devices. It has a very extensive documentation and demo library, and it is the second best established quantum computing framework out there after Qiskit. And so it has a very large community. It's very well spread, and the consideration that I had here in that project, and by the way, that project was funded by MyTax, ETS, and Calcul Québec during my research internship last winter. And what we were trying to do is basically make a bridge between two frameworks, a one-way bridge, so that people can use the PennyLane, which is a very well-established framework again, and they can interface with Monarch, which is using a small rudimentary framework called Snowflake. Another goal, those are secondary goals that has been achieved yet, that have been achieved. Retrieving the results seamlessly so that if I'm switching from Monarch or Simulator or another device, I retrieve the results in a similar fashion so that I can compare my results, do some benchmarking and whatnot. And I wanted also to ensure that we can support all subroutines in PennyLane, so all the circuit building features, we can support them, and we can send those operations towards Monarch. So we don't have to build big circuits from the ground up. So my approach here, and this is on the opposite side of the spectrum, this is way more classical software development methods. I had to understand a typical execution stream in Snowflake and a typical execution stream in PennyLane. Understand how we build we build a job really in both frameworks, and both use a similar method of building a job. You first define your device, so which device you'll be using, what type of hardware you'll be using. You will construct your circuit in either an object or a function, and then after that, you'll execute your circuit and retrieve your results. In PennyLane, you've got a couple classes, but this is really what there is to it. You've got a Q node that's a wrapper for a quantum tape and a device. The quantum tape is your circuit, and the device is the hardware you'll be using. So the Q node, as I said, is a wrapper that's attached to a function, so that when you call the Q node, it's building a Q node object, and when you're calling the function, it calls the execution method from the Q node, and that way you can just call your circuit, and you'll get the result right away without having to build your Q node, build your device, passing your Q node in a parameter. So really what we're trying to do is slowly trying to build it in a higher level. But the size, if I may, the size of the hardware is basically it. And the quantum tape is, as I said, the circuit. So when I'm creating my my function, or I'm defining my operations, when I'm using my my decorator or my wrapper, that function is gonna build a quantum tape, which is basically just a vector of operations, a list of operators, and a list of measurements. So the type of measurements I want to get out of my simulation or my job on real hardware. And then you'll have the device, and that's where my work began. Pennyline is providing an interface, which is the device, which all the other plugins are inheriting from, so that you can have a start for your work, and somewhat of a template. And yeah, that's where I started my work. And Snowflake, you've got a similar fashion. You've got a similar architecture. So you've got your quantum circuit, which is the object that has your operations again. And you can either instantiate a virtual QPU object, virtual quantum processor unit, which is basically a simulator, or you can instantiate a real hardware with your credentials, so that you can then send your job and then retrieve your results. So quantum circuit, again, is the object that's defining the hyperparameter, so the number of qubits that I want, number of bit. So again, as I said earlier, we're really low level. I'm basically creating registers here. Then I'm constructing a vector of instructions, and I've got some functions that can help me with that. Then after that, I've got basically three types of functions to either do simulations or actually send a job towards a hardware. And feel free to stop me at any point if you've got questions. The QPUs itself, as I said, you can have your simulators and you can also have your actual hardware, which you need to provide some credentials. So when I started my work, I had to ask myself what kind of classes I want to use, and it all started with the structure that is very similar to what I had in those two frameworks. So I had to start with a device, so that will inherit from the interface that's provided by Pennyline. So I could create a device that would have the responsibility to deal with entry points when I'm calling the device and instantiating in Pennyline. It's a device that will be executing the circuit, and it's a device that will do some pre-processing. For example, if I have operations that are not recognized by Snowflake but are coming from Pennyline, it will do some pre-processing so that those are understandable for the device. The converter here is really just taking the circuit as is from Pennyline and is recreating the quantum circuit in Snowflake, so that after that I can interface with Julia. Then after that, I could have created a compiler as well to optimize my circuit. That is actually in the work right now, still in Calcul Quebec, in a second research project, also funded by my tax. And if I have access to the API, I could also create a class that would deal with such calls and deal with the states of my job in the cloud. Currently, when I created the project, I did not have access to the API, and I didn't have interest into creating that. So the granularity that I chose to go with was just basically starting with a device, starting with a converter, and then after that, I would iterate from there. Myself, again, very classical. I had to get familiar with Python packaging because, again, in the quantum community, there is a lot of physics and mathematics researchers. We want to make it easy for them. We want them to have to deal with environment and such things, at least as less as we can. So just Python packaging, allowing them to use the Python package manager, pip, as you may know. So that's basically what I had to do. I had to figure out some CI/CD as well, so that I can just do some releases on GitHub, and then it goes on PyPy, allowing researchers to access to the newest version of the package. And the current state of the project, I am still employed in Calcul Quebec, working part-time while pursuing my studies here. So what I've done is we can recognize the device here and the pin lane converter, which is converting and interfacing with Julia. And what I've done is before I had all my measurements in the converter, because as we've seen earlier, the quantum tape comprises the operations and the measurements. What I've been trying to do is separate those two, because measurements can either be simulations or real jobs on hardware. So they really need different strategies, different algorithms, and different scripts to just process with a same circuit. So once I've got my circuit that's rendered in Smoke Theory, then I can use different strategies to interface with either a simulator or Monarch itself.
All right. Thank you so much
For having us.